Kinan-db. Should I restart? All right, hi everybody. I'm happy to introduce Kinan-db, who will be presenting his work on K9db, privacy compliant storage for web application by construction, that recently appeared in OSDI 2023. Kinan is a PhD candidate at Brown University, advised by Malta Schwarzkopf. Kinan builds systems and tools to improve end-user privacy using every tool possible, from computer system, cryptography, and programming languages. His work was cited in the United Nations Guide on Privacy Enhancing Technologies and the White House's 2023 National Strategy to advance privacy preserving data sharing and analytics. All right, Kinan, take it away.
Okay, great. Thanks for the introduction. Cool. So hello, everybody. My name is Kinan, as Rawan mentioned, and today I'm going to be presenting our work on K9db, a privacy-compliant storage for web applications by constructions. This is joint work with all of the wonderful people whose names are on the slide from the Ethos group at Brown University. And as Rawan said, this work just appeared at this last OSDI. Cool. So in recent years, we've seen a surge of privacy and data protection laws, including the EU's GDPR, the CCPA in California, among many, many others. And because of this, application developers must ensure their applications comply with these laws to avoid heavy fines. One particularly challenging requirement that is common in all of these laws is mandating that applications must allow users to access or delete their data. And this is the primary focus of the work I'm presenting today. These laws also generally mandate that applications take reasonable steps to secure the data, and this is often interpreted to require encryption at rest. Our work also satisfies this. Now, privacy laws have many other stipulations, such as around user consent, cookie banners, purpose of processing. A lot of these are simpler from a technical perspective, and they are out of scope for this work. Okay, so let me start by convincing you that achieving compliance with these aspects is actually challenging. So let's look at the following scenario. Let's say we have Alice, the user of some application, and let's say Alice requests deletion of her data as in accordance with the GDPR. Now let's wear our developer hat and try to design a mechanism that satisfies such requests. The first thing that the application developer needs to do is to identify Alice's data in the database. And this is really challenging in a real-world application because applications often have complicated schemas that have many tables and many relationships. And so this often ends up being a sort of very complicated, very intensive manual set of queries that the developers have to write that does all the right joins and all the right filtering just so that it can identify the data. Okay, but let's say we do that. Is that it? Well, not really, because some of this data that we just identified, some of Alice's data, might be related to other users as well. And now the developers must determine how to handle this data. This is application dependent. It depends on the application logic. It depends on the sensitivity of the data in question. So for example, perhaps it's okay to retain Alice's chat messages that she exchanged with some of her friends, but not to retain sensitive medical records that she shared with a doctor. Then developers also often need to retain some of Alice's data, maybe in some anonymized form, for legitimate purposes that are allowed for by the law. For example, retaining anonymized financial transactions for tax purposes. And finally, developers must update the caches and backups that contain data from Alice. And remember, any mistake in any of these steps might cause the application to become incompliant and therefore face heavy fines. Naturally, the developer is now freaking out, but unfortunately, the traditional SQL databases that we're all used to are not really helpful. They shift the burden of compliance entirely onto the developer, as we just saw. Our work introduces K9db, a compliant by construction SQL database that handles access and deletion requests, as well as other compliance invariants that are required by the GDPR and other laws, as built-in primitives. This results in a happy developer and better data privacy and control for end users. Let me pause here and see if anybody has a question before moving on with the rest of the talk. Okay, fantastic. I'll move on. K9db's main goal is to help developers get compliance right. We do so while requiring little application developer effort and few application changes. And K9db does so while exhibiting performance that is comparable to widely used SQL databases, which, remember, they offer no built-in support for compliance. In this work, we assume that applications and their developers are honest but fallible. We aim to reduce the burden of compliance on developers and avoid costly bugs. We believe this is a reasonable assumption because the penalties imposed by laws are usually sufficient to deter malicious behavior in many, many cases. In this work, we encountered three main challenges. These will outline the rest of the talk. First, K9db must capture application-specific compliance policies, especially around shared data and anonymization. Second, K9db must enforce these policies correctly when handling access and deletion requests. K9db must also ensure that any invariants that are required for compliance always hold. And finally, K9db should achieve all of this with good performance. To address the first challenge, we design a set of high-level schema annotations that developers use to express their desired policy to K9db. K9db internally represents this policy as a data ownership graph, or DOG for short. So let's look at this in more detail. Here's a look at a typical application scenario that has users whose information is stored in the users table, send direct messages to each other, and the messages are stored in the messages table. Importantly, note that every message has two foreign keys that point to its sender and its receiver. The first thing to note is that the records in the users table correspond to human end users. In other words, data subjects in privacy legislation terms. These human end users or data subjects have rights to their data under the privacy laws. And so, for example, Alice or Bob or Carol, any of these users, should be able to request access or deletion of their data. The application developer expresses this fact to K9db by annotating the users table with the data subject annotation. K9db allows applications to issue two new SQL commands or primitives, GDPR forget and GDPR get, for complying with GDPR deletion and access requests. Application can issue such commands only targeting rows and tables that are annotated with data subjects. Okay, let's look at what happens if Alice requests deletion of her account under the GDPR. Let's say that when Alice does this, the application issues this GDPR forget command that I'm showing on the slide. Now, let's say we have two messages in the database that are related to Alice. The first she sent to Bob, and the other she sent to Carol. Let's say there's a third message there that is also unrelated to Alice. The developer is now faced with a policy decision. Specifically, what should the developer tell K9db to do with the messages that Alice exchanged with other users? One example of a reasonable policy here is joint ownership, which is in fact what Facebook and many other applications do for direct messages in practice. According to this policy, a message should only be deleted when both its sender and receiver request deletion of their account under the GDPR. The developer expresses this policy decision by annotating both the sender and the receiver foreign keys with the owned by annotation. Giving these annotations, when Alice requests deletion, K9db retains all the messages. However, if in the future Bob requests deletion, then K9db deletes the message that is shared between Alice and Bob, but keeps the other messages because they're related to at least one active user, in this case, Carol. Now, one thing to note here is that even though both Alice and Bob have, in this scenario, left the application and deleted their account, their surviving data still has information about them. In this case, their username, for example. This is a case where some form of anonymization may be needed. Concretely, if you actually use Facebook and you've sent messages to some other people on Facebook, if any of these people that you sent messages to have since deleted their account, you will notice that Facebook displays your conversation history with them as if they are a deleted user. They do not show you the username for that. It just says deleted users, and it shows you a gray sort of generic avatar, not actually their profile picture. Now, developers can express this to K9db using anonymization annotations. Here, these annotations instruct K9db to set the sender column to null when the sender requests deletion of their data, and do the same thing for the receiver if the receiver requests deletion. In this example and in the rest of the talk, I am mostly focusing on account deletion because I think it's easiest to understand why it's important. But K9db and these annotations also include access requests, where users request a copy of the data about them from the application, not deletion. K9db provides more annotations, which you can find in the paper. And these include additional anonymization annotations, including anonymizing data when users request access, not just deletion. It also provides annotations to specify that users have access, but not deletion rights to some data. And in total, K9db provides 7 new annotations. And the important thing is that developers can use different combinations of these annotations to express a wide range of policies. This includes alternative policies to the example joint policy we saw before, including policies that dictate that messages should be deleted as soon as either the sender or the receiver requests deletion, or that messages should be deleted only when the sender requests deletion and the receiver is irrelevant, or vice versa. Okay, I'll have another short pause here just to make sure nobody has any questions. Good. Okay. Now, in real applications, these policies can get a little complex, especially if the schema is large. And so K9db provides an explain compliance command that helps developers get the annotations and the policy that they specify right. This command displays information about what the current annotations imply in a developer-friendly format. And it has some heuristics baked in for detecting potential annotations errors and issues warnings or suggests fixes to the developers where it encounters any of these. Now, internally, K9db represents the policy using a data ownership graph, or DOG for short. And it deduces the DOG from the schema and the annotations. The DOG is a multi-graph where every node represents a table. And the DOG must contain at least one data subject table, which we highlight using a double circle on the slide. Edges in the DOG correspond to annotated foreign keys, which carry some ownership semantics. The edges always point towards the data subject table, either directly or transitively, even when the underlying foreign key points in the opposite direction. Here's an example of a more complicated DOG, which corresponds to a social media application scenario. The DOG highlights a couple of important patterns. First, we have shared data, which has more than one owners. And also, we have a chain of edges, which represent transitive ownership. Rows in the tagging stable indirectly refer to their owner via the corresponding story. The DOG specifies which data K9db should return or delete in response to an access or deletion request. And the DOG is suitable for this because of 2 very important properties. First, starting from a row in some table, for example, taggings, K9db identifies all the owners of this row by traversing the outgoing DOG relationships transitively until it reaches the data subject tables. Conversely, starting at a data subject row, K9db identifies all the data owned by that data subject by traversing all the edges in the opposite direction. Now, we just saw that the dog can act as an effective specification for how to handle GDPR access and deletion requests. Now, let me convince you that the dog and our annotations are actually flexible enough to support other kinds of scenarios, not just the one I showed you. So let's look at one more example here that represents a common pattern that we encountered while studying several real web applications. In this example, we have three tables: users, groups, and members. The members table associates users with the groups that they are a member of. Let's try to annotate the schema and see what the doc for it looks like. The first obvious step is to annotate the users table with the data subject annotation. So now we have this currently unconnected dog, and we're going to add the annotations to sort of add the missing connections to it. The second step is to annotate the user foreign key in the members table with owned by. This is intuitive because a user owns the fact that they are a member in some group. If the user requests deletion of their data, the records of their memberships of various groups should also go away. Now, finally, let's say we want to make the groups themselves owned by the users in them collectively. We can try to do this by annotating the group foreign key in the members table with owned by. However, this results in something that is a little nonsensical, and in fact, K9db rejects it outright. Because this makes the members themselves, the records in the membership table, owned by their group instead of the other way around. What we need to do here is we need to flip the directionality of this edge in the dog so that it points in the opposite direction, making groups owned by members, and then members in turn are owned by the users, and so transitively the groups will be owned by the users. We can do this with the owns annotation, which instructs K9db to assign ownership in the opposite direction to the foreign key. Note that this also changes the cardinality of this ownership relationship, because now we have many members that own a single group, because it's the opposite direction of the foreign key. This is a common pattern that abstractly encodes a many-to-many ownership relationship between the users and the groups that they are a member of. Okay, good. So we just saw how K9db captures application compliance policies and represents it using the dog. Now, let's look at how K9db actually enforces these policies to achieve compliance via a new ownership-aware storage layer. The storage layer is organized according to the dog and has built-in support for access and deletion requests. K9db stores data organized by its owners. What that means is that the K9db storage layer consists of a collection of per-user microdatabases that each contain exactly the rows owned by the corresponding user. K9db can do this because of the dog. For example, if a new row is being inserted into K9db, K9db uses the dog to identify who owns this row, and then inserts the row into the corresponding microdatabases. K9db also similarly relies on the dog to handle updates and deletes to ensure that the contents of the microdatabases are always consistent with the dog. One important consequence of this design is that K9db stores copies of jointly owned data in the microdatabases of each of its owners. This seems unorthodox, but it actually offers three advantages that are critical for compliance. Let me show you what these are. First advantage is that this design actually simplifies handling access and deletion requests of shared data. For example, when Alice requests deletion of her data per the GDPR, it is sufficient to remove her microdatabase because that's where all her data is. Second, this allows K9db to use a different encryption key per each user. And this is important because this guarantees compliance in the presence of encrypted backups. If Alice requests deletion of her data, it is sufficient to delete her key, which causes backups of her data to be in effect deleted because you can't decrypt them anymore, the key's lost. And the final advantage is that there is a challenge here, which is that regular application operations may violate compliance. For example, by disassociating data from its owners, making it orphaned. With this microdatabases design, K9db can detect and reject such violating operations so that it ensures that compliance is never violated. For example, any orphaned data cannot be stored in any microdatabases, and so it is easy to detect when it occurs. I'll demonstrate what I mean by this using an example. Let's say my lab, Ethos, has a WhatsApp group where our graduating students share pictures from this past graduation, including this very nice photo of nearly everyone in the lab that we are using as the group photo. Now, say I am a part of this group along with my advisor, Malta, and many other students. Okay. Now, as people graduate and move on, they leave this group. So the membership, the members of this group is always in flux, right? New people come in, people leave. One potential pitfall here that WhatsApp really needs to avoid is that if everybody in the group decides to leave it, and the group now has no members, zero members, that the group and itself and any associated resources like the group photo should not remain stored in WhatsApp's databases. This is because such a zombie or orphan group would not be associated with any users, and so its resources cannot be deleted by any GDPR requests from any users. Right? This is incompliant. If this were to happen, they would probably get fined. Let's dive a bit deeper into this scenario. Here's the dog we saw earlier from the example with the users, groups, and members. And let's say in this example, we have two users, Malte and I, and we are both members and thus owners of the Ethos WhatsApp group. And remember, according to our microdatabases design, K9db stores two copies of this group, one in my and one in Malta's microdatabases. Good. Now, let's say that WhatsApp issues a delete, removing Malta's membership in this group. I want to emphasize that we're talking now about a regular application operation. This is not a GDPR delete. This is merely an application level delete, right? Malta opens the UI, goes to the group, clicks on the leave group button. Okay. So how does K9db handle this delete statement? The first thing it does is that it deletes the corresponding row in the members table. Okay, so that's easy. But then K9db identifies that the members table has an incoming edge in the dog that comes in from the groups table. And this means that operations that on the members table affect who owns the different groups. And so to handle that, K9db cascades to the groups table, identifies that the Ethos group is no longer owned by Malta because the record of that ownership just got deleted. And so it removes that group from Malta's microdatabase. K9db then finishes handling the operation and commits it. And this is great because notice that the soundness and the completeness of these microdatabases is preserved. The data in every microdatabase corresponds exactly to who owns that data. Okay, so this is fine. This is okay. However, let's say in the future, I also decide to leave this group. And now WhatsApp issues this new deletion statement, this new deletion operation that deletes my membership in the group. What does K9db do? The same thing as before. First, it deletes the row from the members table, and then it cascades onto the groups table and removes the group from my microdatabase because I no longer own it. Now this is the problem, because now the group itself is no longer owned by any user. This also means that it has no microdatabases that K9db can store it in. And so the group is orphaned. And again, as I said before, such orphaned data can cause incompliance because for orphaned data, no users can request deletion of that orphaned data. Good. So K9db identifies this and rejects this deletion operation that the application issues. It does not commit it. It throws an error. And the DB remains unmodified and it remains in a compliant state. Good. So compliance is preserved. Now, K9db rejects this operation because it's not clear, given the lack of context, whether this operation is the result of some bug or omission in the application code, or whether this is intentional. So an example where this could be intentional is maybe this deletion statement is part of a procedure that first removes the last member from the group and then follows it up by deleting the group itself. Or maybe it adds a different member to it or something like that. Such sequences are very common in web applications, and we do not want K9db to reject them outright. To support such sequences safely in a way that guarantees that compliance is never violated, K9db provides compliance transactions, or CTX for short. The compliance transaction is sort of intuitively very similar to a regular SQL transaction, but is more to do with making sure that the compliance invariants are never broken. So a compliance transaction wraps several application operations inside of it. And these application operations are allowed to temporarily violate compliance, e.g. by creating orphan data, let's say, as long as the transaction restores compliance prior to committing. So for example, K9db accepts the compliance transaction, the CDX on the slide, even though it initially makes the ethos group orphaned, because later it goes back and deletes that group. Now, of course, if this transaction was mistaken, if there was a bug there, and the second delete wasn't part of the transaction, then K9db would have refused to commit the transaction. Good. Now, the last detail here is that we just saw that even a single sort of simple application operation, such as a point delete, ends up being translated to many sub-operations over different microdatabases behind the scenes. And K9db executes all these sub-operations inside a transaction, which ensures that all the updates are atomic. In our implementation, in our prototype, these transactions have repeatable reads isolation, which is the default in most SQL databases, such as MySQL. And indeed, we found that any weaker isolation level cannot guarantee compliance, because if you have sort of two transactions occurring concurrently, they might race to sort of try to modify some data and end up causing data to be orphaned without realizing because of a race condition. Now, the paper discusses several of our storage layer optimizations, including allowing K9db to just avoid cascading altogether in many cases, by relying on things like foreign key integrity and other optimizations. And if you're interested in that, I encourage you to check the paper out. Okay. Now, before I move on to some of our implementation details and optimizations, let me stop again just to make sure that nobody has any questions.
I have one question, Kinan.
Go ahead, yeah.
Sorry, back maybe to the original users and messages table. You talked about how you can annotate a policy for the individual user to indicate what should occur, the owned by on that, so that they are nulled. Actually, yeah, there was a little bit earlier. So you can indicate that the ONDEL, yes.
Mm-hmm.
So is it that K9db will ensure that you don't leave a dangling primary key? So for example, if you didn't have the ONDEL, then the sender owned by might reference Alice, but Alice is no longer in the users table. So is that prevented by K9db as part of the logic?
Yeah, that's a very good question. So basically what you're asking about here is sort of foreign key integrity, right? Like sort of some referential integrity in SQL databases. And yes, K9db, ensures that you have referential integrity. If you're issuing some operation that causes referential integrity to break, the operation won't go through, you'll get an error. So perhaps in a way, this was a bad example. But the point of this example, you're right that there's referential integrity here that might, protect you regardless of this annotation. But not everything that you want to anonymize is a foreign key. Like, for example, maybe you want to anonymize the body of the message itself. Like, you don't want somebody leaving sort of their name inside the message or something like that. And so this is the sort of thing that these anonymization annotations help you with. Right? So you're absolutely right. You will, if this annotation wasn't there, we would run into sort of referential integrity issues.
Okay, thank you.
Yeah, good. Okay, so let me go back to where we were. Okay, great. All right, so I'm not going to go into a lot of details about sort of our implementation and our optimizations. I'm just going to highlight a couple of important things just in the interest of time. If you're interested in anything else, feel free to sort of ask me questions later, or we can take it offline, or read the paper, or whatever else you want. Okay, so the first detail I want to talk about here is how we actually implement these micro databases. And our K9db prototype, the way it does this is it realizes all of them over a single RocksDB data store. RocksDB is a key value store. It's a very popular sort of storage engine, a storage backend engine that powers up all sorts of applications, all sorts of things. And we're using it. The reason we're doing it this way is because by having all the micro databases be in a single store, we can actually use secondary indexes the same way that most SQL databases use them, and also things like RocksDB iterators, snapshots, and transactions. And all of these features allow us to handle queries quite efficiently and also achieve asset guarantees. With regards to the asset guarantees, like I said before, we get the guarantees that are similar to sort of the default guarantees in MySQL. This includes repeatable reads isolation. And this is the case even if you have operations that affect multiple micro databases or multiple tables or whatever. And our prototype implementation consists of about 35,000 lines of C++ code, and then a little bit of Rust and Java code in there as well. Cool. The second optimization is that K9db serves complex queries from an integrated in-memory cache, which is based on materialized views. K9db updates this cache after every write. This includes both regular application writes, things like deletes and inserts and whatnot, but also includes GDPR deletion requests. And because of this, the cache is guaranteed to always be up to date and always be compliant, because it's automatically updated and maintained by Kinan. The reason we do this is we've noticed that web applications often end up caching some complex queries in memory just to speed things up. And by providing that cache in an integrated way inside K9db, we allow developers to reap the benefits of caching without having to maintain the cache themselves or ensure that it remains compliant. Because even if the database is sort of compliant and the data is deleted, if that is not actually reflected in the cache, then the application as a whole won't be compliant. Good. So let me talk about some evaluation here, just to show you sort of a hint of what the performance of K9db is like. We evaluated K9db using several real-world applications. And in our evaluation, we looked at three important questions. The first one is, what is the impact of using K9db on end-to-end web application performance? The second is, what is the effect that K9db design features and optimizations have on performance? And lastly, how much application developer effort is required to use K9db? We evaluated the first question based on two real-world applications, Lobsters, which is a link aggregation and discussion board somewhat similar to HackerRank, and OwnCloud, which is a file-sharing application somewhat similar to Google Drive. Both of these applications are open source, which is why we chose them. Now, in the interest of time, I'm just going to show the result for our for Lobsters, and you can find the results for OwnCloud in the paper. In this experiment, we generate a load that is derived from the actual load that you observed in the actual deployed Lobsters. And this load corresponds to 9 common endpoints, such as reading a story, opening the front page, posting a new story, and what have you. The x-axis on the figure I'm showing you shows the endpoints, and the endpoints on the left are read-heavy and more common, while the ones on the right are write-heavy and rare. And the y-axis here shows the median latency, and so in milliseconds, and so lower is better. The first thing we did is we took our harness, our load, and we ran it against our baseline with sufficient enough load so that the hardware is saturated. This harness here is a multi-threaded, it's open loop, it just sort of issues many requests in parallel, and we've increased the requests as much as we could up until the hardware was saturated. Now, for our baseline, we chose MariaDB, which is a popular fork of MySQL. And the reason we chose it is because it also supports RocksDB as a storage engine, just like us. So this makes the comparisons sort of make more sense. Now here you can see the results for K9db. And the high-level takeaway here is that K9db is achieves compliance with similar performance to the baseline. And remember, the baseline has actually no built-in compliance support. Let's look into this in a little bit more details. You'll notice that for the endpoints on the left, which are read-heavy, K9db outperforms or matches MariaDB. And that's primarily due because Kinan has in-memory caching, and so it caches some of the complicated queries automatically. On the other hand, for the write-heavy endpoints, you can see that K9db is competitive. And it's not much slower. The overhead here in the median is, I think, for in the worst cases, about 4%. Not a lot, given that you're getting compliance sort of for you know, you know, because it's giving you compliance, and this is why it's costing you this 4%. So that's entirely reasonable. Okay. Now let's look at the 95th percentiles. Now let's look at the tail latencies, and here the picture is a little different. You can see that in the tail, K9db now has somewhat significant overheads, especially in the writes, but also in this comments endpoints, which is not write heavy. So what is going on here? So in order to understand this better, we ran the same experiment, the same load, against an identical version of K9db with encryption disabled. So it's the same thing, it's microdatabases, everything is the same, but just does not encrypt the data prior to writing it to disk. And we found that encryption is actually a significant portion of this tail overhead. One thing is that this MariaDB baseline actually does not encrypt data by default, because again, it doesn't do anything related to compliance. The developers need to do it. So for example, the tail latency for the comments endpoint that I'm showing here, this corresponds to cases where we're retrieving comments on stories that are very popular and have thousands, if not more, comments. And so K9db must perform thousands of decryptions for every one of these comments individually as it's retrieving them. And this sort of overhead of encryption is in line with some of the related work that I will discuss later. For example, there's this thing called GDPR bench, which was trying to sort of figure out exactly what the overhead of achieving compliance with the GDPR is. And they've actually identified that encryption is one significant place where overhead might occur. Now, encryption is a fact of life. You sort of have to encrypt things, and if you want to comply with these laws, encrypt them at rest when you're storing and writing them to disk. But hypothetically, let's say the developers still did not want to exhibit this overhead. One thing they could do here is they could accelerate this endpoint by caching some of the queries in it using the K9db in-memory cache. Because the cache is in memory, it does not actually need to be encrypted according to GDPR. So that the cache is unencrypted. Good. So I just showed you that K9db has comparable performance to sort of traditional SQL databases to MariaDB. That's great, but in the comparison I just showed you, K9db had an unfair advantage because it uses in-memory caching for the expensive queries, while the MariaDB baseline does not. It just computes all the queries against the database directly. So to have a fairer comparison, we looked at a specific scenario that we extracted out of lobsters, out of this application. In this scenario, we have two operations. We have writes, which corresponds to a user upvoting a story, and reads, which corresponds to counting the numbers of votes that have been assigned to a particular story. This read query performs an aggregate with a group by, which would sometimes be cached in a web application because it could be expensive. In this experiment that I'm showing you here, the load is 95% reads and 5% writes, with a Zipfian distribution over the stories being voted and retrieved. And this is sort of, these are the common parameters that represent real web application loads. Now let's start with the median latencies, and let's look at the results for both the previous baseline MariaDB, but also this new baseline MariaDB with memcached. That is a very common sort of in-memory caching setup that a lot of web applications use. As you would expect in the median, the reads that use a cache are faster, right? That's not a surprise. But obviously this comes at the cost of additional overhead on writes, because when a story gets a new vote, the cache entries that correspond to a story has to be invalidated. So there's additional work on writes. The effect of caching is relatively small here because this query is sort of not the most complicated query in the world. Sort of, it has a group by, it's a bit complex, but it's not that expensive. In the paper, we have other experiments from a different application from OnCloud, where the queries are far more complex, and there you see sort of more separation between the caching baselines and the non-caching baselines. Okay. Now here are the results for K9db. And as you can see, the read and write performance it offers are very comparable to Memcached. There's a bit of difference in the write, but this is mostly an implementation detail. The cache is integrated in K9db, and so updating it is sort of part of the same process. While in the case of MariaDB plus Memcached, it's an extra RPC, because the Memcached is you write to the database and then you invalidate Memcached using it's a separate process, so you have an RPC. It's not really meaningful, just an implementation detail. Okay, now let's look at the 95th percentile tail latencies again. And notice that here, the reads, even with the caching baseline with MariaDB plus Memcached, the reads are actually now slower than MariaDB. And the reason this happens is because the tail, in this case, the 95 percentile tail, corresponds to cache message. Right? So we're trying to count the number of votes for a story that is not in the cache, because maybe it has been invalidated due to somebody actually voting for that story. But in the case of K9db, we have no cache message, because K9db is based on materialized view. The caching in K9db is based on materialized view, and the cache is always up to date, because K9db performs additional processing on the write to update the cache and make sure everything is always up to date. Now, of course, there is no free lunch. We're fast on the reads, but then on the writes, you can see that we have a little bit additional overhead because we are performing more work. We are actually keeping the cache up to date as opposed to just invalidating the cache and removing the entry from the cache. We believe this is a very good trade-off because web applications generally are pretty read heavy. And so, significant savings on reads pretty much justify some additional amount of work on writes. And I want to remind you all that in addition to having this better read performance because of having no cache misses, a key advantage of this whole caching approach that we have is that the cache is always up to date and is always compliant, because K9db is automatically updating it in response to all the writes, including GDPR deletion requests. And so the application developers here do not need to take on the responsibility of making sure that this cache is compliant or worry about it in any way. Cool. Now, in addition to sort of the previous experiment, which is about runtime, about latencies, we also measured the memory overhead that we require for our caching. And this measurement is for the entirety of lobsters, not just the one query that I showed you before. Now, using Memcached with the on-demand caching setup, caching adds about 1.6 the times of the database size in memory overhead. Now, with K9db, this adds about 3.3x the database size, or about twice the size of Memcached. This is because K9db needs to store additional state inside its sort of data flow processing engine, because it needs that state to ensure that the cache is always up to date. And these numbers that I'm showing you here are more or less in line with the memory overhead numbers that are reported by other works that also use data flow-based materialized views, things like Noria from OSDI 18. Cool. Now, the paper addresses the other evaluation questions that I posed to you in the beginning. We have other experiments that are based on workloads from OnCloud, file sharing applications, which also show comparable performance to both MariaDB and the MariaDB plus the Memcached baseline, the caching baseline. Our results also show that the K9db storage layout optimizations are critical for achieving good performance. And finally, we found that K9db can capture the compliance policies for 10 real web applications that range from social networks, e-commerce applications, to conference submission systems. One common challenge we encountered while migrating those applications to use K9db is that several of them have schemas that are not normalized. Web application developers are sort of horrible for having very hacky schemas. And so a lot of these schemas, did not have explicit foreign key constraints specified in them. For example, you would have a column, it would be basically a foreign key, but it wouldn't have that foreign key constraint. And we needed to sort of reverse engineer all of these different relations in order to first understand the schema so that later we can annotate it and make it use K9db. And one thing we've observed, which is slightly surprising, is that as part of this process of understanding the schema and annotating it, K9db ends up guiding the developers to making their schema be sort of well-designed, normalized, which was very surprising. And the tools that we provide in K9db, including this explain compliance command that I mentioned earlier briefly, sort of helps the developers along this way and holds their hands as they make the appropriate changes. Cool. Now let me briefly mention a couple of important related works. The first one I want to talk about is Delph, which is Facebook's deletion framework. This is a system that is used by Facebook actively in deployment for both deleting data, regular data deletion that is sort of part of Facebook's features. You post a comment or something, and then you change your mind and you delete it, that sort of thing. But they also use it for user account deletion, which is basically their way of responding to GDPR deletion requests. Now, Delph requires that developers specify their deletion policies declaratively. And specifically, what they have to specify is whether to cascade or not cascade some deletion, certain deletions between related objects, such as, deleting a post, does it cascade into deleting the comments or not? And this part of Delph has been, I like it a lot personally. It's like something that inspired us. It inspired the annotations the way that we define them. Although our annotations are a bit different because we're concerned with SQL, with relational databases. In the case of Delph, it's something else entirely. Now, as I said, I really love Delph. I think it's a great paper to read. And if you're interested in this topic, you should read it. There's a lot of interesting conceptual and also engineering challenges involved in getting it to work at the scale of Facebook. They have, backups and geographical sharding and all sorts of stuff, network failures, all sorts of stuff that they have to take into consideration. But with that said, with all of this praise, Delph is only just a deletion framework. And while deletion is required for compliance, it is not the whole story. So Delph, for example, does not support user access requests. It does not have any built-in support for compliance invariants, such as ensuring that you never have orphan data. There's no compliance transactions, nothing like that. And it also doesn't provide support for encryption or caching or even assisting the developers in sort of ensuring that the policies that they specify is indeed compliant with the law and not some sort of made-up policy that doesn't quite work. Good. The second important related work is GDPR Bench. And this is interesting work. It actually translates and interprets some of the legal articles of the GDPR into technical requirements. And then it tries to comply with these requirements, their interpretations of them, using existing databases, especially Redis and Postgres. And the philosophy in this work is a bit different. They wanted to make minimal and intuitive changes to these systems, not to redesign them as a whole or change them significantly. That was their guiding principle. And given this philosophy and given their particular interpretation of the law, the GDPR bench found that compliance causes very significant overheads, mainly due to encryption at rest, but also because of the added metadata tracking that they needed in order to attribute data to its owners. In the worst case loads in their work, these overheads exceed 5x reduction in throughput and about 6x space overhead. So these are quite a bit high overheads. These are at odds with K9db. We don't sort of have any overhead. Our overheads are very minimal. They're nowhere near those. Because K9db is fundamentally different. It actually is a big fundamental change in terms of how the database is organized and stored. It's not just minimal changes. And because of that, we don't exhibit the same metadata explosion or extreme overheads that you see in GDPR Bench. And the last related work here is Schengen-DB. This is a proposal for a system design that does indeed provide GDPR compliance. But it's a bit of an interesting and strange design. It relies on some expensive metadata tracking and quite coarse-grained enforcement and it results in significant changes to how the web applications are even developed and operated. So for example, part of this proposal is to sandbox data that belongs to different users in different VMs during their processing, and then destroying those entire VMs when a user requests deletion. So I think it's quite interesting, but maybe not so practical. And finally, there's a bunch of sort of less related and mostly orthogonal works, but I'm putting them here for completeness and because I think there's interesting connections with them. First thing is we've seen a lot of new systems in recent years that try to enforce privacy policies. So stuff like an application will not use a phone number that a user gives them for two-factor authentication. It will not take that phone number and then use it for marketing. Things like that. Things like making sure that the computations are in line with the consent that the users give. These include systems like PrivGuard and RuleKeeper. They're very interesting, and I think this is an important aspect for sort of overall compliance with GDPR and other laws. But they're orthogonal to our work. These are not storage systems. These are systems for data processing that include some sort of static analysis or dynamic policy check component to it. Interesting, but orthogonal. The other sort of interesting and also somewhat orthogonal thing is decentralized platforms, things like Solid and Web3 ideas. These are interesting, but they change the structure of web applications drastically because they rely on having users store their own data on their own machines or on VMs they control rather than on remote services. And this is a little related because if a user truly is storing all of their data in a machine they control, then deletion and access requests become trivial. Now, of course, there's more complexity here because what if data is shared between different people? Then how do you delete it if it's under the control of some other users? So there's some interesting work to be done here. And finally, we have encrypted databases, things like K9db and Mylar, which go way above and beyond the simplistic encryption required by GDPR, and they have a much stronger threat model. And we also have sort of cryptographic privacy enhancing technologies, things like MPC, fully homomorphic encryption, differential privacy, etc. And these provide very strong cryptographic guarantees about either the security of the computation itself or the privacy or the leakage of the outputs of the computation, let's say in case of aggregates. And both of these technologies are orthogonal to our work and to some extent orthogonal to the GDPR. But the reason I'm including them here is because I think there's a lot of interesting interplay that we should all be studying between the guarantees of technologies like this and what the law requires, or even systems like K9db. Cool. So let me conclude here. We presented K9db, which is a database that helps developers get compliance with the GDPR and other privacy laws right. K9db relies on the data ownership graph, the DOG, which is the key abstraction that captures compliance policies of real applications. And it also relies on a new ownership-aware storage layer, which was organized into per-user microdatabases. K9db achieves compliance while exhibiting performance that is comparable to traditional SQL databases, which offer no built-in compliance support. Our code is available at GitHub, and thank you a lot for listening. Cool. So if you have any questions or if you want to have some discussion, let's do that now. Okay, I see many hands raised. Let's go in order. Valentine, your hand is there. Okay.
All right. Well, thanks for the talk. It was very cool. I was wondering, it's a bit of two questions. Is there any support for letting the user know whether they're enforcing certain parts of those policies correctly? And also, like, the other question is, like, is there room for mistake when you're implementing those policies?
Good. Yeah, these are good questions. Let me take the second one first, and then I'll go back to the first one. Room for mistakes. This is interesting. There's, conceptually, there's multiple places where mistakes could happen. One thing that could happen is maybe our system has a mistake in it, like it tries to delete something, but the code is buggy or something like that. This might be indeed the case. This is, after all, research, sort of academic code, but we have a lot of tests. Part of the reason we design it this way is because the deletion procedure is actually so simple that mistakes are unlikely.
Oh yeah, I meant more mistakes from the user when they implement the schema.
Yeah, good. So yeah, so that's more interesting. I think the developers, the application developers, not the developers of K9db, might make mistakes in how they phrase their annotations. That is something that is indeed could happen. And we have some tooling that tries to guide them along, but most of what we have here is basically heuristic based. So it's not like a foolproof guarantee. With that said, I think the chances of the developers making a big mistake annotating the schema is far less than the chances of them making a mistake if K9db did not exist and they had to do all of this work manually, because it's like orders of magnitude more code that they have to write, orders of magnitude more complexity that they have to sort of keep in mind. Remind me again of the first part of your question.
It was whether there was some sort of like meta-analysis that could analyze your schemas to tell you whether there are mistakes.
Yep. Good. So I think that also we addressed, right?
Yeah, I think so.
Good. Okay. Let's see who else. David, your hand was also raised from before.
All right. So my question was, how much replication do you have in your benchmarks? So one of the things you said was that if you have shared data, it ends up replicated, and that replication is not free. And so, the more you have, it's going to change the performance, probably for the worse, but at least change it.
Mm-hmm.
So I was wondering how much of that there was in your experiments, and if you did any performance analysis of the consequences.
Yeah. So the application I showed you, the Slopsters thing, there is limited replication there because most of the data there is not truly jointly owned by multiple people. There is sharing going on, but it's mostly I own something and then I share it with people. They have access to it, but they don't fully own it. They don't control it. They don't delete it. And so there is no duplication happening behind the scene. The one place in that application where duplication is happening is private messages because they're owned by both the sender and the receiver. But overall, there is, it's limited. The space overhead is limited. The other application we have in the paper, OwnCloud, has more duplication in it, or sort of more truly shared data because it has groups, and then the groups are owned by all their members. That sort of thing. But I do want to point out that in general, I think data that is truly shared, truly jointly owned by multiple people, not just sort of shared in like a read-only access way, is not super common. Like it certainly exists, but it's rare. In the application scenarios that we looked at, we never really identified data that is sort of jointly owned by more than 3 or 4 different users at any given point in time, right? And this is very important because if you have some data that is sort of duplicated 2 times, 3 times, maybe it's okay. But if you have data that is in your application, you have data that is truly jointly owned by thousands of users, then probably our system, sort of performance-wise, wouldn't work for your case anymore.
Mm-hmm, right.
But again, that is a very rare scenario. We have not encountered anything like it in our investigation.
Okay, thank you.
Okay, Abirman, you have your hand raised.
Hey, this is Alex. Question about implementation, if I may ask. You mentioned that you used RocksDB to implement the ownership storage and manage. What did you use to implement the main storage engine? And related question, what is the definition of atomic transaction in this case? Do we need to complete the write into, for example, do we need to complete the write into the main storage and the ownership part, or just the main? And how do we accomplish that? Did you modify somehow how, say, write ahead log works?
Right. Yep. These are great questions. So perhaps I was a little bit vague and maybe confused you a little bit with me, but we don't have sort of two storage, right? Like we have just a singular storage system. It's RocksDB. That's where we store the data. That's our primary storage. But if you think of RocksDB, it basically is like a key value stores with like column families, right? That's sort of how it works. What we do is think of your SQL database abstractly. It's like a bunch of tables. So, okay, usually every table would be like a column family or something like that. What we're doing is if the table is owned, data in the table is owned by multiple people, we're copying it into multiple column families. So there will be a column family for you, a column family for me, a column family for whoever else. And the data that is owned by me will be stored in my column family. Data owned by you will be stored in your different column family, right? Think about it at a high level that way, to some extent, right? And if we have data that we both own fully, then we will copy it. The system copies it twice, stores it once in my column family, once in your column family, right? That's not exactly how it works. It's a bit, we have a bit more optimizations on top of that. We didn't want to create, a ridiculous number of column families. That's going to make the system slower. But at a high level, think of it that way. Okay, so that's the first part. And with regards to transactions, I think now, given what I just described to you, the difficulty is not that you have to sort of update multiple storage engines, like a primary one and an ownership one, anything like that. The difficulty is that if I'm trying to update a row and that row is copied and stored in 3 different column families, I need to update it in all of these 3 ones, and I need to update it atomically in the sense that if there's a concurrent read happening, that read should see either the result prior to update or the results sort of post the update, right? I don't want to have a scenario where one of the copies of the row has old data and then the other copies has new data, and both of them are visible to concurrent operations, right? And we didn't really need to modify the writer head log or any sort of super details inside RocksDB for this. We just sort of used some of the features that RocksDB already provides. Like it has transactions. They're pessimistic. They're locking based, but it has these transactions. They perform well enough, and we use them.
Thank you.
Cool. Okay. Any other questions or comments?
I have one if nobody else does. And that is, I had an idea just now, which is that if you did have something with 10,000 owners, you might store it in its own micro database with a session key and then 5,000, 10,000, or however many access keys for that session key. Have you thought about that? Does your system support anything like that? How hard would it be?
Yeah, that's a great question. So we're thinking of sort of like extensions or alternative designs along that direction. I think what we're trying to do is perhaps there's a way to not have to store these copies. The reason we store the copies is because it simplifies deletion, fine, but I'm sure we can get the deletion to work even if there wasn't copies, even if it was some sort of logic, like the copies were more or less a logical view. We can still get deletion to work. What is truly an issue here is encrypted backups. I want to be able to make sure that the backup itself becomes unusable, even if the backup is like in an Arctic vault somewhere, or like even if I don't know where the backup is, because like God knows where the backups are. And the current design that we have, you just throw the key away. And because your data is encrypted with your key, you throw the key away, the data is gone, even the backups are gone. Without the copies, this becomes harder, because if data is shared between 2 people, which of the keys do you throw away? Do you throw both of them away? Do you throw one away? Like, what do you even encrypt it with? There's just one copy of it. So this is sort of what we're looking at. I think our idea right now is basically something to do, think of onion encryption. Like if the policy was, if any of 3 users request deletion, some data gets deleted, then you can encrypt that data in sort of an onion encryption with 3 keys. 1 key belongs to each of these users. And if you lose any one of these 3 keys, the onion as a whole doesn't decrypt. Maybe the outer layer decrypts, but some inner layer doesn't decrypt or whatever. That works fine. The policy that is more tricky to do is saying that it should be deleted when all of them delete, right? After everybody deletes. Onion doesn't quite work there. And so one idea we have is maybe we come up with like a new key for such like such data. And then that key is encrypted with my key, with the key of the other people that have access to it or like own it, right? And we store like encryptions of that key. And then when I want to delete my data, the encryption of that key that corresponds to me goes away. But if other users stay in the system, their versions of the key still is there. So something like that. But it's quite tricky to get it to work in a way that is performance friendly. Because if you have to do multiple layers of decryptions every time you're reading data for regular application operations, you're introducing more and more overhead. And like I told you, encryption is already sort of one aspect where this overhead is perhaps could be significant if we make the encryption more complicated. And so, this is what we're grappling with right now.
All right.
Yeah. Cool.
There are no other questions. Let's thank our speaker. All right. Well, thanks, Kinan. This was a wonderful talk. Right.
Great. Okay, perfect. Nice
Thank
talking.
you.
See y'all.
Bye.